Next, Joe student. So, real one. Okay. Who is also the organizer? Okay, so we are very happy to have Anton Nedelin, and he will talk about superconformal indices from superconformal indices to elliptic integrable models and back. Please.
Thank you, Maxim. So, as Maxim told, I'm another student of Joe, but Alessandro started his story like about how he first met Joe, and Joe asked, who are you? I don't know if it's true, but the point is that I didn't start as a student of Joe. And my first encounter was like, I was in Uppsala. Joe was this semester. When I started, Joe was teaching at MIT for one semester. I didn't see him for first half year of my PhD. Then Joe appears and we meet on the kitchen, where else? And Joe says, oh, I've seen your paper. This was my master project, basically, about some solitonic solution, which was very condensed matter inspired. And he said, oh, it looked cool. And I was just fresh PhD student. So I thought, oh my gosh, someone cares here about my work. But this is Joe. He always had, and what struck me, like the genuine interest in what other people do. I think he reads all the papers of people from Uppsala, which I don't think other professors do, to be fair. Don't take it personally. I mean what I mean. And you can but at least, I don't know, it's always, you have something to discuss with Joe about what's going on in physics, and not only in his field. And in fact, I liked it a lot. And at some point, we started working with him on one project. Unlike Alessandro, I wasn't so unlucky. We finished it. And then I switched to Joe being my primary supervisor and finished as Joe's student. And we had 3 years of enduring PhD, 3 years, which were pretty fruitful collaboration. And sporadically, it was happening also after I finished, like these 2 papers. And of course, there were also papers which Joe discussed a lot with me, and then I published without him. And as Alessandro told you, it still continues sporadically. Hopefully, I will balance out this Alessandro tendency not to finish projects with Joe, and we will publish it. Okay, now I will come back to things about Joe in the end of my talk. Now I will proceed with science. So I will talk about my work with what I was working lately for several last years, together with Shlomo Razamat mainly, but also with other collaborators, Hichol Kim and Bilal Nazal. And there are several papers, including one which is work in progress. So what is it about? This is very general setting. When you have supersymmetry is a powerful thing, and it often happens that observables in this in different supersymmetric field theories and various dimensions with various amount of supersymmetry, they are dual or they are related in some way to integrable models. Not in a sense, most people are talking on this event, not in a sense of some beta equations or n=4 super Young Mills, but more like in the spirit of Nekrasov-Chitashvili, what is called BPS-CFT correspondence. And I will be talking about less general thing and more concrete setting. For us, the object which we will be studying will be superconformal index in 4 dimensions. And this will be superconformal indices not of any theory, but of class of theories that can be obtained compactifying from 6-dimensional superconformal field theories. It was found quite long ago, like in 2012, that there is a relation of superconformal indices with introduction of codimension of surface defects to some integrable finite difference operators. And in particular, one particular setting which was well studied before, the single one basically, is when we start with 6D 2,0 theory, we land on class S theories in 4D, and then the dual integrable model is Rusinar's Snyder model. That's what was studied in this paper. And then in subsequent papers, mostly details of this correspondence were studied. And this is a useful thing. It's not just for fun. Fun is, of course, the primary goal, but it's a useful thing for calculations because it allows to compute indices of non-Lagrangian theories in 4D, which is exactly usually the theories which arise in these compactifications on Riemann surfaces. And okay, for example, one of the first theories where it was applied to was Minahan-Nemechansky E6 theory. So here is contribution of Joe. Many people here are talking about Joe's contributions to integrability, of course, but Joe has very important legacy in supersymmetric gauge theories, which maybe was not noticed at first, but once AGT corresponders appeared, people appreciated a lot these works. Okay, so this is the setting which we will be working with. Okay, now I'll go to explanation of how the construction of integrable models work. So again, a little bit of generalities. We start with some 6-dimensional superconformal field theory in UV. We put it on Riemann surface. The Riemann surface can have some punctures. It can have flux of the global symmetry turned on. And we flow to some 4-dimensional supersymmetric quantum field theory in IR. Sometimes it happens that this 4D theory has also UV description in 4D. In this case, there is a Lagrangian description, but not necessarily. And this is very general. Of course, you've heard the story. I give you some more recent reviews of this, lecture notes about all this business just for the reference, but you, of course, learned this story already. So this is not talk about compactification. So the only things we need to know are what are punctures. So for us, punctures is a very simple thing. There's, of course, this Guyota classification of punctures. It's complicated subject, but for us, it's basically some objects which bring with them the global symmetry. We assume that we will be considering only such cases when there is 5D compactifications in terms of gauge theory. In this case, and with Lagrangian, and in this case, puncture is just obtained by putting boundary conditions on these 5D compactifications, and some global symmetry appears, as well as some set of special operators, which we refer to as moment map operators. They are not really moment map. It's more like terminology that was taken from 2,0 story. Here we're more general. We can glue punctures by just gauging this global symmetry and identifying these moment map operators. And we can also close punctures by breaking this global symmetry, and we're doing it as usually you break symmetry by giving VEF to some of the operators charged under the global symmetry of the puncture. We can do it like give VEF to moment maps itself, but we can also give it to derivatives of the moment maps. And it will be important. Okay, the object observable, which we're considering for the theories, is superconformal index, which is just you put your theory on S3 cross R, you quantize it on S3, and you compute such kind of traces. Where you put fugacities for each of the global symmetries you have. You have global symmetries associated with spin 4, which is G1 and G2. You have R symmetry. You have some global symmetry, some flavor symmetries in your theory. For each of the symmetries, you turn on the fugacity, and this fugacity is bookkeeping mechanism to see. Basically, we compute trace over S3, so we sum over all possible BPS states in your theory, and we can trace which BPS states comes with which charges. And using localization, or if you're in 3D, use it also, you can go to UV-free theory and compute this index. So not in this form, but to reduce it to some, basically, matrix integral. And work with this. I won't write this matrix integrals here. It's complicated expressions, which won't give you much idea anyway. But you can do it. You should just know it. So at the level of the index, we can do all the puncture operations which I mentioned 2 slides ago. We can glue theories, but this corresponds, as I told you, to gauging global symmetry of the puncture. So we take indices of 2, for this we take indices of 2 theories living on 2 Riemann surfaces. And if we glue these surfaces, we just integrate it with appropriate measure. Measure depends on the particular details of your compactification. In this very simplest case, you can imagine it will be just contribution of the vector multiplet, which is given by this expression where this is elliptic gamma function. And you can close the punctures. This is a little bit more complicated operation. So you give VEF to certain operator. This operator contributes to the index with certain weight. And everything boils down in the end, after some lines of arguments and calculations, to computing residue of your indices at certain positions. So the index have certain analytic structure which contains certain poles, where you have the poles are located at the values which correspond to the weights of certain operators. If we give VEF to them, we should compute the residue at the corresponding pole. And P and Q comes because you give VEF to derivative rather than to operator itself. Because P and Q are fugacities of spin 4. Okay, right, and if, one more thing, if we give VEF to the operator with derivatives, this introduces certain profile in space-time, and you expect that this is some codimension 2 defect introduced. This is hand-wave argument, what I said now. It was shown in detailed computation in this paper by Gadde and Gukov. Oops, okay. Now, how do we derive our integrable operators from the index? So we have 2 working assumptions. One I mentioned about them. Basically, first that you need this 5D reduction to be Lagrangian theory. For this, you need to have good description of the puncture, which we can work with. And second is that there is 4D Trinian theory, which also should have Lagrangian description. Trinian is basically compactification on the sphere with 3 punctures. That's it. Here I denote different types of punctures, but these are details. You don't even need to know it. Now, what you do, imagine you start with some compactification on some Riemann surface, which corresponds to certain index. First, you introduce extra puncture, and you introduce it by gluing this trinion to your original Riemann surface. So basically, you start, if you glue, this puncture goes away, but 2 new punctures come. So in this way, we have 1 more puncture, and then we close it, giving VEF to these derivatives of the moment map operator. So in the end, we arrive, of course, you need to be careful with the fluxes, because the flux of what you started with should be the same as flux of what you end up with. All these operations change the flux of the global 6D global symmetry, but you arrive to the same Riemann surface, but physically, if you give VEF to derivatives, you also have some defect introduced. Okay. And at the level of the index, if you mirror all this computation and compute all these residues and the things I told you, what you often arrive to, it's not a proof or anything, it's just empiric observation. You often arrive to the following type of expressions. So your index, which you obtain after all these operations on the right-hand side, equals your index on the left-hand side, on which you act with certain type of finite difference operators. And there is the original paper where all these things were noticed, and then we have more recent paper where we have a good review of these things with more details of this construction described. These operators have these operators, H, which I introduced here, they have 2 important properties which you get for free without any proof or calculation. They just follow from 4DS duality. At the level of this Riemann surface compactification, basically this 4DS duality tells us that we can move punctures around freely. And one property is that all these operators commute with each other. So we get not 1 operator, but there is this index alpha. We get tower of operators. This tower of operators comes from different M and N indices. So I now take away this m and n and just leave one, I have only one index left to denote this tower. Basically here I depict how you prove it by moving around punctures on your event surface, but basically it doesn't matter in which order you act. So we get the infinite tower in principle of operators which commute with each other, which is usually, when you see such things, you start thinking about integrability. Though, of course, you need to prove if operators are independent and all this kind of things. Second property is property which in physics maybe we're not used to it. It's called kernel function property. And but mathematicians find it very exciting because it helps them in understanding the properties of operators. And this is the following property. It's not what you would think it is from the name. It's kernel function. You expect that you act on function and you get 0, I guess. But it's not. You get the function of several variables, and imagine you have these operators which we derived, and they can act on the several variables. So you first act on the first variable, and then you act on the second variable, and in principle you can have more, and you always get the same expression. And in this case, we say that this function is a kernel function of these operators. And the claim is that all superconformal indices obtained in certain compactification are kernel functions of the operators we derived in this using this compactification. Again, just follows from S-duality. I pictorially depict it here. You take this puncture which you close, and you move around closer to one or another puncture. And you get this property automatically. Okay. Now, how is it useful for indices? Assume we know the spectrum of operator. Not always true, unfortunately. But let's assume that we know the spectrum. Lambda is some eigenstate label. It can be integer, it can be partition, as it often happens. And these eigenfunctions are orthogonal with respect to this gluing measure, delta, which I introduced previously, and which depends on details of compactification. The natural ansatz for kernel functions looks like this. Is just for each puncture which our Riemann compactification surface have, we take one eigenvalue, we take the product, and we sum over all eigenvalues with some coefficients. What is special here, of course, these eigenfunctions, they form the basis, but what is special is that there is only one sum, because of course, if you have a function of many variables and you expand it in some orthonormal basis, you expect multiple sums for each of the variables, basically. But here we have single sum. It's diagonal expansion in this basis. Okay, and as a simple example, okay, let's say that lambda has some natural orderings, like lengths of the partition, for example, or if it's integer, it's just integers are ordered already. Then for two-point function, for tube, for example, compactifications on the two-punctured sphere, we get this simple expression. So it's just this thing. Now, I will show you a small algorithm which we came up with in this paper with Shlomo and Bilal on how this can be used in order to at least get hint on the spectrum of your integrable operator if you don't know the spectrum, because spectrum of many of these operators are not known. They are complicated. You start, okay, I went a bit further. You start with a tube, but this tube should either have some flux or it should be compactification on some higher genus surface, like I put here on torus with two punctures. So it's not really a tube, it's a two-punctured compactification. And now let's start gluing them together, many of them. If you glue it n times, that's what you get, just by orthogonality of eigenfunctions. The only difference is that these coefficients, which we don't know, they get into power n. Now if we take n, yeah, sorry, one more thing. We consider everything, as we usually do in indices, in expansion in this parameter, pq, or p and q. And there is assumption in our calculation, which is checked by self-consistency of the result, that these coefficients, they are their expansion in this parameter y, meaning like the first coefficient is of order 1, second is of some order in the y, third is even higher order in y, and so on. So they start at certain order in y, and this order they start in is growing with which coefficient you take. And if we take n very large and take expansion in this y parameter, then C lambda, this lambda naught, the ground state coefficient, is dominant in n to infinity limit, and we're left only with the ground state wave function. And in this way, we can just do this computation for the index, do a lot of gluings, and use these formulas to derive ground state coefficient and ground state wave functions from here, but as expansion in this parameter. So it's like perturbative calculation. It's not full eigenfunction. And in principle, if your spectrum is non-degenerate, which is never the case, you can also derive higher eigenfunctions and eigenvalues as well. Okay, now I gave you some background, now a little bit of examples of what we were doing. One example is, of course, Ruijsenaar-Schneider, but it was considered before us. But recently, there were a lot of progress in n=1 compactifications, of 1-0 series compactifications in 6D. So one of the examples is E-string theory, which is like the theory which lives on M5 brane probing D4 type singularity in 6D, and it has E8 global symmetry. This is 6D global symmetry. So it was shown that there are 3 possible 5D compactifications which have Lagrangian, and hence 3 possible puncture types. And these puncture types comes with the global symmetries of SU2. Sorry, here is everything is SU2. You would say, okay, what a lame way to write it. But actually the point that 4D compactification depends on which kind of root system you take, because first of all, these root systems are generalizable to higher rank. Also, descriptions for AN, CN, and A1 power n are known, but this is not this E-string theory, it's already deconformal matter. And trinion compactifications with A1 puncture, it has simple description in 4D in terms of SU3 SQCD in the middle of conformal window. So with 6 flavors, and on this quiver diagram, I split these flavors into 6, and here 6 is split in, so 6 fundamental or anti-fundamental, and 6 fundamental are split into 2, 2, and 2. Each 2 is corresponds to the puncture with a global symmetry SU2. So punctures here have SU2 global symmetry. If you take C1 or A1 powers 1 compactification, the quiver won't look like that. The compactification is different. Okay, then we run our algorithm, which I described in the first half of the talk, and we land on the integrable model, which is known. It's BC1 Van Dijk operator, it's called, and it looks something like that. So you see it's a shift operator. You shift with your X is basically your SU2 variable, which you act on. This is fugacity of the global symmetry of the puncture. And you have some bunch of theta functions. And there is some constant part, which is just elliptic function with certain pole structure. So it has 8 parameters of the Van Dijk model, and these 8 parameters physically are identified with 8 moment maps, which each of these SU2 punctures have. And it's known to be integrable. So this is one example, and we can, of course, nothing is known about spectrum of this Van Dijk operator. It's certain deformation of Ruijsenaar-Schneider, and things are not very well known for Ruijsenaar-Schneider to start with. So let's try to say something about ground state at least. So this is our 2-punctured sphere theory. So it's just bifundamental and 8 chirals. Cross is the flip field, whatever. Index looks like that. It's super simple index, just a bunch of elliptic gamma functions. A gluing measure is this. So there is vector contribution, but there are also 8 chirals actually, but okay. There is also some matter multiplets. And for simplicity, let's put all this HI, which I remind you are charges of the moment map operators, to the same value. Then we can derive perturbatively the wave function. It looks ground state wave function. It looks something like that. So eigenvalues we derive by just substituting wave functions back into our eigenvalue equation. Unfortunately, Van Dijk operator is so complicated that everything we get from such a complicated wave function is just this. Going higher in orders is very complicated in this calculation, unfortunately, but this is more of a computational problem which we in principle are trying to overcome. Okay, this was one example. Do I have time for another? You're not showing me the... Okay, I have 5 minutes. Okay, another example is something more exotic. There are things in 6D which are called minimal 6D SCFTs. The point that if you put... so assume you want the SCFT in 6D with no matter content, then you have certain anomaly cancellation conditions, and not everything is allowed in this case. And basically, what is allowed is that your 6D n=1 theory that flows in IR and 6D to gauge theory with gauge group G, and only these groups are allowed. So it's finite family of 6D superconformal field theories. So Lagrangian descriptions in 4D of compactifications are known for these two theories. Nothing is known for F4 and exceptional groups. And I will stop today on SU3, the simpler one. So SU3 compactification punctures have SU3 global symmetry. It's coincidence, they're not the same. Because here it's some gauge theory, it flows in 6D, and this is 5D compactification. For example, if you take SO8, the puncture symmetry has SU4, so it's different. So Trinian theory is trifundamental hyper. Here is the quiver, like 3 punctures here with SU3 symmetry. Index is quite simple. It's just trifundamental. It's just a bunch of elliptic gamma functions again. Tube theory, you can obtain closing one of those punctures, and you get collection of 3 bifundamental multiplets. Again, index is here, and gluing measure is also very simple. It's just vector multiplet. Unlike Van Dijk, we don't have, or unlike E-string, we don't have any matter here in the gluing measure. Okay, you run your algorithm. So first, Shlomo did it alone, actually, and he obtained this operator. It's one operator. One is in principle not enough in this case, because you have, so this is integrable model for 3 particles, basically. Coordinates of the particles correspond to your fugacities of the SU3 global symmetry of the puncture. And there were a lot of puzzles with it, which I will tell you in a minute. And recently we basically did nasty job and arrived the full like tower of operators, which look like that. Of course, this operator, it looks nice. It's something similar to Van Dijk. There is some shift operator and just 4 theta functions as coefficients. Here you have a lot of theta functions if you go higher in operator. Okay, as I told you, there are some problems here. And problems are mostly associated to this parameter y. This parameter y is not in your field theory. I mean, when I wrote you, sorry. Yeah, it doesn't. Okay. When I wrote you these things, you see this capital Y was not here. So your field theory compactifications don't have this parameter, but it appears in computation of the integrable model. And they are nasty. So as I told you, okay, they are not in the kernel functions, but they're an operator. Operators with different Y commute. So instead of tower of operator labeled by integers, we have some infinite amount of operators. which are commuting with each other. And ground state wave functions, as we found with Shlomo, they are not known, but we found using our method. Ground state eigenfunction is independent of y. So your operator depends on this parameter, but ground state wave eigenfunctions do not. And then, of course, in the ground state energy, the y dependence factorizes completely, which makes sense because your ground state wave function is not dependent on this parameter. Okay, so, and there were also some other subtleties which I will talk about on the next slide. So how did we resolve them? Also, Ruizenars actually he got interested in these operators. He tried to study them. He proved some of the things which we knew from the index computations, but didn't push it further. So the resolution is quite simple. Apparently, this operator, which we derived, it's not one operator. It's sum of two commuting operators, and 2 is enough for three-body system to be integrable. So actually, one operator was everything we needed. But finding this factorization is very non-trivial. We managed. We guessed it from some. We first guessed and then proved that it's correct. And there are two operators. So one operator is a sort of elliptic generalizations of the Toda system, which we didn't see in the literature. But what I mean by elliptic generalization is that I can take certain limit where it becomes just Toda. H2 is just a known operator, but they're commuting and they look to be two faces of the same system. And if we look on the fusion rules of operators, which is important, usually in the fusion rules, you expect of these operators, because they correspond to certain defects, you expect it to be fusion rules for representation of your root system, like representation of A2 in this case. But you get something completely different. Looking on these expressions, you can see that these two operators, H1 and H2, is everything you need to construct the full tower of operators. So you don't need anything more. So our integrable system is actually this one. So this is our latest result, and we are now studying, this is work in progress, we are now studying basically properties of these guys. Okay, so let me come to conclusions. So I tried to convince you that there is cool correspondence between superconformal indices and certain class of integrable models, which can help us actually in computations. It can both help us in computing things in physics, like indices of non-Lagrangian theories, and in math, like things like perturbatively computing spectrum of these integrable operators. And there are plenty of work to be done. There are more minimal 6DS CFTs at least. There is things like rank QE string theory. So in principle, there is a swampland to be explored here. Okay, and here I finish. I want again to congratulate Joe. And you ask questions, and then I come back to saying something about Joe.
Thank you. Oops. So, any questions? Questions?
Hi. I wanted to ask you, what is this kind of quantum integrable system come out also as a quantization of cyber-Witten curves in 5D, right? Like, for example,
Yes.
And what is the relation between...
Good question. We thought about this question, but we don't have convincing answer. Moreover, if you noticed, one of my co-authors, Hichol Kim, he's precisely author of these papers where they do it, for example, for E-string compactification, and they derive Van Dijk model. The funny thing, they did it also for deconformal matter, for another thing which I mentioned here, and we have different models there. So it has the gist of that this should be related, but we cannot quantify it, unfortunately. Yeah, it's a good question, but no answer, sorry.
Thank you.
Any other questions?
Thanks for the great talk. You mentioned one of the assumptions in the construction of these operators is that you start from a trinion which is Lagrangian. And we know that the vast majority of trinions do not have this feature.
Yes, and then where...
Do you know if there might be, like, they correspond to extra operators or maybe something...
No clue, that's the
fact
point.
that it is Lagrangian, because it seems the fact that it is Lagrangian is crucial to derive the action that it has on the index.
Yeah.
But the other things will have an action as well. But it's just that it might be difficult to derive, but still you expect to have operators of this type. The commutativity will hold on and...
Well, yeah, that's a good question, but again, that's unstudied realm. I mean, they maybe exist, but how would you come to them, you know? Because you cannot even write any index to start with. If you don't have Lagrangian description for the trinion, even writing any indexes. There are, however, there is one example where I can tell you. Okay, so there is rank Q E-string compactification. Rank Q E-string compactification has known tube compactification with Lagrangian description, but no trinion. From tube compactification itself, if you jump into math literature, there is a great mathematician, Eric Ryans, who by some reason is interested in all these elliptic functions. I don't know what his motivation is, just I want to study them. And he, even like before anything was known about all these things, he derived that what we will say now is that this tube compactification of rank QE string is a kernel function of BCN Van Dijk model. So hence, this is exactly the case. We don't have trinion description. We don't know how to derive, but we know that there is BCN Van Dijk model. So probably they are, but it's very hard to say something except this one case.
I was going to ask you on the, so on your A2 example, so you had this unknown operator.
I spoiled.
You had this H2 operator, and you said it was unknown.
Yes, not unknown. Okay, we don't know. Yeah. Yeah. Okay. I mean,
you have it, but yeah, I guess I was trying to figure out what you meant by it, because it looks like you know what it does, but you don't.
No. I mean, unknown in the literature, but it doesn't have the name. It doesn't. It's not related to any operator that we know. Yeah. Sorry. I mean, that's why I said it's not unknown. We know it indeed, as you said. It's not known in math literature. So this one we managed to relate in certain limit to Toda. On itself, this form is also something that we didn't find in the literature. While this H2 in the same limit, we took basically physically this is 3D limit. When you go from S3 cross S1 to squash 3 sphere, then this operator becomes Toda, but this operator becomes something, I don't know. Not very complicated operator, but we didn't find anything. I asked ChatGPT, it doesn't know as well.
It's integrable.
Well, integrable, we don't know it for sure. I'm very frivolous in calling all it's integrable. They commute, like probably they're integrable, but usually in this business you arrive to integrable in operators.
Okay, any other questions? If not, let's thank Anton.
Yeah, okay, and as I promised, a little bit more about Joe. So, unfortunately, in our Eurostrings conference, which I was also involved in organization, we didn't have time in the schedule to expose you to Swedish culture. And who else would do it as non-Swedish living in UK, right? Most appropriate person. So there is a famous, at least in Sweden, Swedish tradition of fika, which is scrambled like word coffee. It's basically a tradition of coffee break, but it also plays more social role. And it's usually practiced in the workplaces. Secretaries in our division had it every day. We had it once per week on Friday at 3 p.m., if I'm not wrong. And Unfortunately, I wasn't able to, as an organizer of the thing, I wasn't able to put myself right before 3 p.m. But okay, you will have lunch thing. So, and the point that Joe, and we loved it as a students, he was passionate about physics and math, and he was coming to this fika with problems, with brain teasers for us to solve. And we were having a lot of fun solving them. And I think this is also shows how Joe is always enthusiastic about science and everything. So he, even for fika, he was bringing us problems. And problems were varying, like close to after summer, it could have been some, you know, first problem of International Math Olympiad or whatever. And I wanted to expose you, all of you, a little bit to it. So you will have Joe's fika brain teaser, but since it's not fika, you will have lunch brain teaser. So I really tried my best, and I think I recovered in my memory 2 problems that he gave, but one I wasn't able to recover completely. I will give you a pretty simple problem. It didn't need to be hard, but just to have fun. It's probability theory problem. So people come for fika. Let's say there are 30 people. That's approximately the amount that we had in Uppsala. But they have seats which are assigned. Basically, everyone here has his favorite seat, but one day one person comes and he forgets where is his seat, and he takes seats at random. The question is very simple. What's the probability the last person arriving will take his own seat? And if you want to spice up a little bit, let's assume that the first person was just nasty and he didn't forget anything. He just wanted to take someone else's seat. These are different problems. The question is the same, though. Okay, and have fun during lunch.
But who will check the answers? You, Anton, will?
No,
collect?
Joe. Were you
Joe.
checking our answers? Yeah, Joe can check our answers.
So, Joe, do you remember the answer for this? Okay, well, you have 2 hours to think something. So Joe will have exam in 2 hours.
I will help.
Okay.
Okay, that's it.
Okay, thank you, everyone.